So in this video, I'm going to be showing you some of the equipment that you use in Lab 1. The most important part is this sensor here. So what this does is it puts out a little sound wave, a clicking noise that you're going to hear. And if there's some object in front of the sensor, it will reflect those sound waves back toward the sensor, and the sensor can figure out how far away the object is. And even better is it can do this in real time if the object is moving, which means we can use the sensor to make a graph of position versus time on the computer screen for that object that's moving. There's two parts to the experiment. In the first part, you're going to be pointing the sensor at a partner, and they're going to walk away and towards the sensor, and you'll make a graph of their motion on the screen. In the second part, you'll be attaching the sensor to the end of a track, and then studying the motion of a cart on that track. So we'll do that later. Now there's a few things you need to be aware of with regard to the sensor. First of all, there's two settings. So on the top of it, there is a narrow beam setting and a wide beam setting. The wide beam setting is better for pointing at your partner, so for people and objects like that. So put it on the wide beam setting to begin with, you'd point it at your partner, they'll walk away and towards the detector, and you'll capture their motion. For the track, it's better to use the narrow beam setting. So you'd put it to narrow beam, you'd clip it onto the end of the track, and then you do your experiment using the cart. But to begin with, you're going to start with it on the wide beam setting so you can measure your partner's motion. Another thing to be aware of is that the sensor has what's called a dead zone, meaning that any object that's within about 15 centimeters of the sensor, it can't accurately figure out how far away it is. So make sure whatever object you're measuring is at least 15 centimeters away from the detector, and as long as it is, then the sensor can measure objects up to a few meters away. And the third thing to be aware of is that the sensor can be fooled by objects that are nearby. So when you're pointing this at your partner, have them walk in the clear aisles between the desks, just so that the sensor isn't going to get confused by a nearby chair or person. Likewise, when you're using it on the track, just make sure that nobody's got an elbow or a book bag too close to the track. Try and keep the area nearby the track clear so the sensor doesn't get confused. So now I'm going to show you the velocity program that you're going to be using this week. So this is the desktop of the lab computer, and all of the programs that we're going to use this semester are housed in this Physics 1100 folder. So you look around on the desktop and find this Physics 1100 folder, open that up, and inside you'll find a whole bunch of programs in there loose, and also a few folders for those weeks when we need to use more than one program. This week we're going to be using this velocity program down at the bottom. So double-click to open that up. And once it's open, what you'll see is that there's a graph over here on the left, and also a data table over here on the right. So when we take measurements, the data gets graphed here on the graph. It will also show up as numbers in the data table. To take measurements, you just click on this Start button, and then you'll hear the sensor start to make that clicking noise, and then you can move your object back and forth, and you'll be able to see in real time what the position time graph of that object looks like. So I'm going to show you this now. I click on the Start button, and then I take my object and I move it towards the sensor and away from the sensor, and I can stop, and you can see in real time what was happening. If you want to take another graph, you just click the Start button again, and it's going to overwrite the graph that we already have. So I'll do that now. I'll click Start, and I'm going to take my cart on the track and actually move it right up close to the sensor. So I actually moved it right in until it's touched the sensor, but you'll notice that the graph went flatline at about 15 centimeters. And again, that's because of that dead zone. So the sensor can't measure anything accurately if it's too close. Now, in some cases, you may want to resize your axes. So if your data is all squished down at the bottom, for example, you may want to stretch it upwards. So I'm going to show you how you do that. But it's a bit of a complex procedure, so I've also put a handout up on the Moodle website so that you can refresh your memory. So to resize axes, what you do is you go up to the top and you click Display, Settings, and by default, you're going to be on the wrong tab, so you actually want to be on this Axis Settings tab. So I click on that, and you go down here to this Extras area, and you want to unselect Lock Origin Position and Lock Scaling. So you deselect both of those, then you click OK, and now if you want to resize your graph, if you hover your mouse over top of the numbers, so not the line, not the graph itself, but over top of the numbers on the axis, your mouse changes shape to sort of a squiggly double-headed arrow, and then you can click and drag upwards or downwards to stretch or squish your graph. And you can do that in both directions. You hover your mouse over top of the number, click and drag to stretch and squish things. If you want to move the whole graph around on the page, hover your mouse over top of the axis, so the line, not the numbers, and you can now drag the whole graph around. So if you needed to see the negative area, for example, that would be useful. So again, there's a handout on the website that shows you what to click to make sure that you can change the shape of your graph. When you're all done with the program, to close it, you just click the X in the corner. It will always ask you whether you want to save the changes. Always say no. So just say no to saving changes. So on the first question in Lab 1, what they ask you to do is you point the motion sensor at your partner and have your partner walk away from the sensor at a constant fast speed. And then you'll have them do it again at a constant slow speed. And both of those motions you're going to capture with the computer, so you'll see it on screen. And they want you to sketch both of those motions on these axes in your lab manual. And then below, you're going to comment on the similarities and differences between those two motions. So you would have your partner walk away from the sensor at a constant fast speed, and then you're going to draw what you saw on the computer screen here in your notebook. And you should draw it with any little bumps or wiggles in the data or any weirdness or curvature because your partner couldn't walk at exactly a constant speed. That's okay. This is a real-world graph. Go ahead and draw in all of the imperfections. So that would be your partner walking at the constant fast speed. You do it again, same graph, for the constant slow speed. So you'd have them walk away, and again, if there's any weirdness or wobbliness in the data, just go ahead and draw it in. So you draw both of those motions on the same graph, and then below, you want to talk about the similarities and differences between these. And the most important one to talk about is how you know the difference between the fast walk and the slow walk. On the next page, they ask you to do something that's actually pretty common for this course, is they first ask you to make a prediction about what you think you're going to see, and then you'll do the experiment and draw in what you actually did see, and then compare the two, the prediction and the actual experimental graph. In this case, they want you to walk left towards the detector at a constant speed. And they say, what would that graph look like? Make a prediction. So since it's a prediction, we want this to be the perfect world case. So no friction, no bumps or wiggles or weirdness in the data. Just draw the perfect world case for what you would expect to see for motion that's coming towards the detector at a constant speed. So you draw that in, and then underneath it, you're going to actually do the experiment. So you have your partner walk towards the detector at a constant speed, and you draw in what you actually saw on screen. And because this is a real-world graph, you do draw in any little bumps or wiggles or weirdness or the dead zone. And then, down here, you make your comparison between these two graphs. And to get full marks, you do want to talk about what's similar and what's different. So for the differences, you can definitely talk about the bumps and the wiggles and the dead zone and any curvature you saw because your partner couldn't quite walk at a constant speed. And for the similarities, it's never enough to say my two graphs look the same. You have to be specific. And I recommend you use graphing language here. So you might say, well, they were both linear with a negative slope or a positive slope or a zero slope. And you might say they both have a y-intercept that's bigger than 0, or they both have a y-intercept that starts at 0. One thing you don't need to talk about, however, is whether these look like they have the same slope. So it doesn't matter if one of them looks steeper than the other because we didn't actually put any units on these. So you don't need to talk about whether one is steeper than the other, but you should talk about whether they were both linear or both curved, whether they had a positive slope, a negative slope, a zero slope, things like that. And you're going to do this for a couple of different questions following this pattern, where they ask you to make a prediction first about what you expect to see, then to do the experiment and sketch in what you actually did see, including any imperfections, and then to compare your perfect world prediction case to the real world experimental case and say what was the same and what was different. So you do that for a few questions, and then things change when you get to question 9. So now I'm going to take you back to the equipment and show you what you do to perform question 9. Now in step 9, things get a little more sophisticated. So you're going to be using the cart on the track and taking measurements of that. So the first thing you do is take your sensor and go to the narrow beam setting, and then you're going to want to clip this onto the end of the track like that. The window of your sensor should be exactly vertical or maybe tilted slightly forward. That gives you the best results for getting data. And again, make sure that the area around your track is relatively clear of objects. Now, before you actually take data, you're going to want to level your track. And you do this every time you're using the track this semester. So you've been given a bubble level. And so what this is there's a little bubble and there's two lines, and when the bubble is in between the two lines, that means that the spirit level is level. So you're going to use this to level your track. You just put it on here and you check whether the bubble is in between the two lines as exactly as possible. If it's not, then down here at the end of the track, where you maybe have a little bit of trouble seeing it, this end of the track rests on the screw, and you can twist the screw to raise and lower this end of the track. So you do that until the track is nice and level. And then you can put your cart on the track. Now the motion that we want to capture for this part of the experiment is a slow exaggerated push and then a release. And we want it to be a slow exaggerated push because when you've got acceleration, which is what my finger is doing, I'm accelerating this cart when I'm pushing it, the position time graph should look like a curved line. So you want a slow exaggerated push so that you can actually see the curvature on the screen. If it looks like it kinked very sharply upwards, then you probably pushed a little too quickly. So go for a slow exaggerated push, and then you release it. And on the release, just make sure that it's going fast enough that it doesn't look like it's slowing down due to friction. So again, slow exaggerated push, fairly quick release. That's the motion you're trying to capture. Now, before you actually take your graph experimentally, you want to make a prediction of what your graph is going to look like. So just to give you some very mild hints, like I said, when my finger is on this, pushing it, I'm accelerating the cart. So that should look like a curved line on the position time graph. When I let go, it's now rolling freely, so it should be constant velocity, and constant velocity on a position time graph should look like a straight line. So think carefully about what the graph will look like from this motion, draw in your prediction, and then you'll do the experiment and compare what you actually saw to what you predicted you would see. Now, most weeks this semester, you'd capture a graph on the screen and you just print out that graph and paste it into your book. This week and this week only, we're actually going to make you do a hand-drawn graph. So instead of printing out the graph, you're going to print your data table, and then you'll graph it by hand, and that gets pasted into your book. You'll also calculate the slope on the rolling part of the graph. That gives you the velocity of the cart. And you'll talk a little bit about what the differences were between what you actually measured for the graph and what you predicted you would see. So for example, in your ideal world case, you wouldn't expect to see any friction slowdown. But on your real-world graph that you measured with the computer program, you may see that the rolling part of the cart isn't totally straight, that there's a bit of downward curvature because it was actually slowing down due to friction. So be on the lookout for that. In the next part of the video, I'm going to show you how you print out your data table using the program. So as I mentioned, most weeks you would just print out your graph and paste that into your lab book. But this week and this week only, we actually want you to print out your data table instead. So this part of the video shows you how to do that. So first of all, this is kind of a nonsense graph that I made. It's not necessarily what you're going to see when you do this part of the experiment, but I'll just use it to demonstrate. So you're going to want to graph about 10 to 12 data points on the rolling part of your graph. So that'll be the linear part. So to highlight just those data points, you click and drag a rectangle on the graph. So you can just click and drag and it'll put a rectangle on and highlight some of the data. So you click and drag to highlight 10 to 12 data points, and you'll notice that over here on the data table, it's highlighting that data also. So this is what we want to print. Now just so you know, when you go to print things, it's going to print the active window. So for example, if I click on the graph and go File, Print, it's going to print out just the graph. And you can adjust this up to 3 copies for you and your partners. Now I don't actually want to print out the graph, I want to print the data table. So I click on the data table so that it's highlighted, and then I can go File, Print, select 3 copies, and then print it out. And this is going to print out in the lab room. Your lab instructor can show you where. But you print out your data, and then you'll get a piece of graph paper, and you're going to graph your 10 to 12 data points, fit a straight line through them, calculate your slope, and then that gets pasted into your report. And then you'll talk about what differences you saw between your real-world graph that you just made and your predicted graph. So for example, did you see any bumps and wiggles? Was it linear with the appropriate slope to agree with what you predicted? And did you see any friction in the real-world graph? In other words, instead of seeing a perfectly straight line here, was there a little bit of downward curvature? So if you see that, talk about it.